For 70 years, we have been living a lie written in the stars, taught in every classroom, and charted in every textbook. For 70 years, we believed we knew the dimensions of our own home. The Milky Way galaxy, we were told, was a sprawling but measurable metropolis of stars, 100,000 light-years from edge to edge. A colossal number, yes, but a known one, a comfortable one. Well, that number is wrong. It's not just a little off. It's not a minor miscalculation that needs a footnote. It's wrong by a factor of 2. Our galaxy is not 100,000 light-years wide. It is at least 200,000, and likely even more. Every star chart, every documentary animation, every single diagram you have ever trusted depicted a galaxy that was only half its true size. We have been living inside a cosmic empire twice as vast as we ever dared to imagine, and the truth of this has only just been revealed. This isn't a story of scientific carelessness. It's a story about the most profound observational challenge in all of astronomy, trying to measure the size of a forest when you are chained to a single tree in the middle of it. Imagine standing in the heart of New York City and being asked to draw its precise city limits. You can't. You are surrounded by an overwhelming jungle of steel and light. Dust and debris obscure your view. You can't step outside for a moment to get a clear perspective. That is our predicament. We are adrift in one of the galaxy's outer spiral arms, 26,000 light-years from the core, drowning in a sea of countless stars and impenetrable clouds of interstellar dust. For decades, the method for measuring our home was deceptively simple. Astronomers pointed their telescopes in every direction and counted the brightest stars. Where the stellar population seemed to thin out, they drew a line. That became the edge. 100,000 light-years, case closed, but it was never that clean. The galaxy doesn't have a hard edge like a dinner plate. It fades, whispering its way into the void. Stars don't just stop. They scatter outwards in ghostly streams and tenuous clouds. And beyond the light, there is the darkness. An immense invisible halo of dark matter, the true scaffolding of our galaxy, extends far, far beyond the last visible star. The old measurements only tracked the obvious, the bright city lights. They completely missed the enormous unseen suburbs that stretched for another 100,000 light-years in every direction. For years, scientists knew something was fundamentally wrong. The data was whispering of a much larger reality. Stars at the galaxy's supposed edge were moving impossibly fast, defying the pull of the gravity we could see. Satellite galaxies orbited at distances that made no sense. The math never balanced, and then the new generation of eyes opened. The Gaia spacecraft, the James Webb Space Telescope, vast radio arrays mapping the hidden, hydrogen clouds, and the whispers became a roar. They all revealed the same shocking truth. The Milky Way was a giant, and we had been measuring its shadow. This discovery doesn't just update a few numbers, it shatters our understanding of galactic architecture. It changes the timeline for our inevitable collision with Andromeda. It doubles the volume of space we must search for life. Every calculation built on that old, comfortable number now lies in ruins. But the most terrifying question is this. If we could be this wrong about the size of our own home, what else have we gotten wrong about the cosmos? Picture this. You're blindfolded, standing alone somewhere in the vast, searing emptiness of the Sahara Desert. Your mission? To draw a map of the entire desert. You can't take the blindfold off. There is no GPS. There are no satellites. All you have is the feel of the sand beneath your feet and the sound of the wind whispering secrets you can't understand. How accurate could you possibly be? That is the impossible task that has faced astronomers for centuries. That is what it is like trying to measure the Milky Way. We are adrift on a tiny rock, orbiting a painfully average star, tucked away in an outer spiral arm. Our view is choked by colossal clouds of interstellar dust in almost every direction we look. The very heart of our galaxy, the brilliant, violent core, is hidden from us, veiled behind impenetrable walls of gas and cosmic debris. With our optical telescopes, the ones that see the universe as our eyes do, we can perceive maybe 10% of the galaxy. The rest is a ghost, hiding in the infrared, in radio waves, and in the absolute crushing darkness. By comparison, measuring our nearest major neighbor, Andromeda, is almost laughably easy. It sits a comfortable 2.5 million light-years away, a perfect celestial specimen laid out for us to study. We can see the whole thing at once, edge to edge, top to bottom. We can photograph its majestic spiral arms, count its ancient star clusters, and map its structure with breathtaking precision. Measuring our own galaxy, however, is like trying to take a selfie from the inside of your own head while standing in a dense fog bank. It's a cosmic paradox. Early astronomers, armed with nothing but light and logic, had no choice but to try. They measured what they could see. They tracked down Cepheid variable stars, cosmic lighthouses that pulse with a predictable rhythm, allowing them to calculate distance. They painstakingly charted the positions of globular clusters, ancient glittering balls of stars that orbit the galactic core like ghostly moons. They built a map, piece by agonizing piece, like trying to assemble a billion-piece jigsaw puzzle while blindfolded. The first true breakthrough came when scientists realized they could listen instead of look. They could use motion. Everything in this galaxy, every star, every gas cloud, every forgotten cluster, is in orbit around the center. They all move at specific speeds, dictated by the gravitational pull of all the mass inside their orbit. If you can measure the speed, you can calculate the mass. And if you can calculate the mass, you can begin to estimate the true size. But this is where the universe threw us a curveball. This is where the comfortable picture of our galaxy began to unravel. The speeds didn't make any sense. Stars at the very edge of the galaxy were moving far too fast. According to all the matter we could see, they should have been flung off into the void of intergalactic space millions of years ago. Something else was out there. Something invisible, something massive was holding them in its grip. It was an enormous halo of dark matter, wrapping around our entire galaxy like a gravitational cocoon. And this is where the old measurements failed so catastrophically. They only counted the things that shine. They saw the visible stars, the glowing gas, the brilliant nebulae. They completely ignored the invisible mass, the dark scaffolding holding the entire structure together. And that single, fundamental mistake is what kept us blind to the true, terrifying scale of our home for almost a century. Stellar streams. The name sounds beautiful, almost poetic. But in reality, these are galactic crime scenes. They are the frozen, glittering evidence of cosmic violence, of murder on a scale that beggars belief. For millions of years, small, innocent galaxies have wandered too close to the Milky Way. Our home, a gravitational predator, grabbed them. It pulled them in, stretched them like taffy, and mercilessly ripped them to shreds. But their stars didn't just vanish. They were scattered, flung into long, ethereal rivers of light that now circle our galaxy like the ghosts of conquered civilizations. Some of these stellar streams are wider than Earth's entire orbit around the Sun. Others contain the light of thousands of stars, all moving in perfect, haunting formation. For decades, we barely paid attention to them. They were just background noise in our telescopes, faint, distant, and seemingly irrelevant. But it turns out, these ghostly rivers are the most honest rulers we have ever found for measuring the true size of our galaxy. Here is why they are the key that unlocked everything. A stellar stream is a pure expression of gravity. Every single star in that stream is on a path dictated by the total gravitational pull of the Milky Way. Not just the pull of the stars we can see, but the pull of everything, the visible and the invisible, combined. If you can trace the path of that stream, you are tracing the shape of our galaxy's gravitational field. There is no guesswork. There are no assumptions. It is pure, unadulterated physics written across the sky. The Sagittarius stream is the most famous of these cosmic fossils. It's the shredded remains of the Sagittarius dwarf galaxy, a victim currently being devoured by the Milky Way. This stream wraps around our entire galaxy, multiple times, like a ribbon on a present. When scientists finally managed to trace its full, breathtaking path, they realized it extended far, far beyond the old 100,000 light-year boundary. The stream just kept going, and as long as it held its form, it meant the Milky Way's gravity kept going too. Then came the discovery of other streams, like GD1, a thin, almost invisible river of stars in the galaxy's outer halo. When researchers mapped its delicate curve, they found something that should have been impossible. The stream was bending and twisting in ways that required far more mass than the entire visible galaxy could account for. Either the laws of physics were broken, or we were missing something truly enormous. It was dark matter. It was always the dark matter. These stellar streams were revealing its presence like invisible ink exposed to a blacklight. The immense gravitational pull that was shaping these rivers of stolen stars was coming from a substance we cannot see, a substance that extends at least twice as far as the last visible star. And what they discovered next was even stranger. They found streams orbiting at distances we had always considered to be true intergalactic space, the empty voids between galaxies, except they weren't empty. These streams proved that the Milky Way's influence, its gravitational empire, reaches farther than anyone had ever dreamed. Our galaxy doesn't just stop. It keeps pulling, keeps claiming territory, keeps asserting its control deep into the darkness. You're looking at the Milky Way, or at least you think you are. That beautiful shimmering band of light splashed across the night sky is nothing more than a skeleton. It's the bright, obvious bones of a much larger, much more mysterious creature. The truth is, at least 90% of our galaxy is completely invisible. The era of dark matter as a fringe theory is over. It is now a confirmed, measured, and mapped reality. We cannot see it directly, we cannot touch it, but we see its colossal effects everywhere we look. We see it in the stars that orbit too fast, in the galaxies that spin without flying apart, and in the way light from the most distant objects in the universe bends around an invisible mass. The evidence is overwhelming, and it points to a startling conclusion. The galaxy you see is just the decoration. The real galaxy is the darkness. Imagine a skyscraper at night where you can only see the illuminated windows, but not the steel frame holding the entire structure up. That's our galaxy. The stars are the windows. Dark matter is the frame. Scientists now estimate that for every star you can see, for all the glowing gas and dust, there is 10 times more invisible mass lurking nearby. This material doesn't just add a little extra weight. It forms a gargantuan halo around the visible galactic disk. It's spherical, diffuse, and it stretches far, far beyond the spiral arms we call home. The old measurements, the ones that gave us that comfortable 100,000 light-year figure, failed because they completely ignored this halo. They ended their map where the visible stars thinned out, blind to the invisible continent that lay just beyond. Think of it like an iceberg. The glittering tip you see rising above the water is the visible galaxy, the spiral arms, the glowing core. But beneath the surface, hidden from sight, is a mountain of ice 10 times larger. That is the dark matter halo. The true size of our galaxy must include both. Researchers are now mapping this invisible empire using a technique called gravitational lensing. When light from a distant galaxy passes near the Milky Way on its long journey to us, our halo's immense gravity bends that light, distorting the image like a cosmic magnifying glass. By measuring the precise amount of that bending, you can calculate the mass of the object doing the bending, and the results have been nothing short of staggering. Our dark matter halo extends out to at least 250,000 light-years, with some measurements suggesting the fainter outer regions reach nearly 400,000 light-years. But here's the twist that haunts astronomers. Where do you draw the line? When does the Milky Way's halo end and the emptiness of intergalactic space begin? There is no official edge, just a gradual, ghostly fading into nothing. For now, we use a measurement called the viral radius, the point where matter is gravitationally bound to us. For the Milky Way, that sits around 200,000 light-years, double the old estimate, all because of an invisible mass we are only just beginning to map. And the strangest part? You are inside this halo right now. As you sit there, the Earth is hurtling through a vast, invisible ocean of dark matter. Trillions of these mysterious particles are streaming through your body every single second. And you feel nothing at all. Our galaxy is not alone. It's a tyrant, surrounded by a court of captive worlds. Dozens of smaller galaxies are trapped in orbit around us, circling the Milky Way like moons around a planet. We call them satellite galaxies, and for decades we fundamentally misunderstood what they were telling us. We saw the largest of them, the Large and Small Magellanic Clouds, as cloudy smudges in the southern sky, holding 30 billion and 7 billion stars respectively. We saw the fainter ones, the Draco Dwarf, the Ursa Minor Dwarf, as little more than distant curiosities. For years, the prevailing wisdom was that these were just neighbors, independent galaxies passing through our cosmic zip code. But new measurements have revealed the chilling truth. They are not just passing by, they are prisoners. They are gravitationally bound to us, trapped in orbits they can never escape, and their silent testimony has completely rewritten our cosmic address. This discovery changed everything, because a captive's orbit tells you the strength of its captor. When you measure how fast a satellite galaxy is moving at a specific distance, you can calculate the exact amount of mass required to hold it in that orbit. More mass means a stronger gravitational leash, allowing for faster and more distant orbits. Less mass, and the objects would simply drift away into the void. The Large Magellanic Cloud, for instance, sits 160,000 light-years away from us, completing one orbit every 1.5 billion years. For it to remain stable at that breathtaking distance, the Milky Way must be colossal, far more massive than the old estimates based on visible stars ever suggested. When astronomers began tracking the orbits of dozens of these satellites, they all screamed the same story. They were all orbiting farther out and moving faster than our old models could possibly explain. The only conclusion was that the Milky Way is an absolute giant. But the most damning evidence came from the victims of galactic torture. When a satellite galaxy orbits too close, the Milky Way's immense gravity begins to rip it apart, pulling stars away in long, horrific trails. The Sagittarius dwarf galaxy is currently being dismembered this way, its stars stretched across the entire sky in a stream that wraps around our home. These tidal tails are the perfect test masses. They trace the contours of our gravitational field, showing where it's strongest, where it weakens, and where the true boundary of our influence sits. By mapping enough of these streams, you map the edge of the galaxy itself, and what scientists found was shocking. The streams from these dying galaxies extended far beyond the supposed galactic edge, reaching out past 150,000 light-years, some even hitting 200,000. The satellites were our witnesses, and their testimony was undeniable. The Milky Way is huge. This had immediate and profound implications. If our galaxy is this large, then the entire local group of galaxies needed to be redrawn. The space between us and Andromeda is smaller than we thought. The gravitational influence of each galaxy reaches farther. Collisions will happen sooner. And here is the most haunting part of their testimony. We are still finding them. Every few years, astronomers sift through the data and find another tiny, faint dwarf galaxy hiding in the dark, orbiting at an even more astonishing distance. Each new prisoner we discover extends our empire's boundary just a little farther out. How many more are still out there, waiting in the darkness? How much bigger does the Milky Way actually get? 200,000 light-years. The number is so vast that it almost ceases to have meaning. Your brain simply cannot process it, cannot visualize it, cannot hold it. It's a string of sounds, a piece of data, but it isn't a distance you can feel. So let me try to make it worse. Light, the absolute speed limit of the universe, travels at a blistering 186,000 miles per second. In a single year, that light will cross about 6 trillion miles. Now, multiply that by 200,000. The Milky Way is approximately 1.2 quintillion miles across. That didn't help, did it? The numbers are still just noise. Let's try another way. If you could board a starship that traveled at the speed of light, it would take you 200,000 years to cross from one edge of our galaxy to the other. Think about what that means. By the time the light from a star on one side of the galaxy finally reaches the other, the entire story of Homo sapiens, from our humble origins as hunter-gatherers to our evolution into a spacefaring species, could have played out and been forgotten multiple times over. Let's scale it down. If our planet Earth was the size of a single grain of sand, the new Milky Way would stretch farther than the distance from the Earth to the planet Saturn. Actually, much, much farther. Or try this. The light you see from a star at the farthest edge of our galaxy left on its journey to your eyes before modern humans even existed. It left before the Neanderthals, before Homo erectus. That ancient light has been traveling through the darkness since our distant ancestors were still learning to walk upright. The scale is designed to break human intuition. We evolved to comprehend the distance of a thrown spear, the length of a day's walk. Our minds never developed the wiring to grasp billions of trillions of anything. But here is where it becomes deeply personal. That incomprehensible size matters to you right now, because doubling the galaxy's width doesn't just double its size. It makes its volume 8 times larger, and 8 times more volume means 8 times more space for stars, 8 times more room for planets. The old estimate of 200 billion stars in the Milky Way is now obsolete. The real number is closer to 400 billion, maybe even more. Every single one of those stars could host planets. Every planet could have moons. The number of potential homes for life in our galaxy didn't just go up a little bit. It exploded. If life is a 1 in a billion cosmic lottery, we just found out there are 200 billion more tickets in the jar. But this new, terrifying scale also changes the timeline of our own cosmic survival. The Andromeda galaxy is hurtling towards us at 70 miles per second. The collision is inevitable. We used to think we had about 4.5 billion years until the chaos began. But a bigger Milky Way means a bigger gravitational reach. The show is going to start sooner than we thought. 200,000 light-years is not just a number. It is our past. It is our future. It is the stage where every human story has ever been told, in one infinitesimally small corner. And we just discovered the stage is twice as big as we ever knew. Andromeda is coming. This is not a theory. It is not a wild prediction. It is a confirmed, measured fact. Our galactic neighbor is racing towards us at a relentless 70 miles per second, and the collision is absolutely inevitable. For decades, the date for this cosmic cataclysm was set, approximately 4.5 billion years from now. You could almost mark your calendar, except those calculations were based on a lie. They assumed the old, smaller galactic sizes, which meant a weaker gravitational reach and more empty space between us and our cosmic dance partner. A bigger, heavier Milky Way changes the timeline completely. Our gravity reaches farther into the darkness, and so does Andromeda's. The massive invisible dark matter halos that surround both galaxies, stretching for hundreds of thousands of light years, will be the first to make contact. And when those halos touch, the collision officially begins. Think of it like two people walking toward each other in the dark. If they are both much larger than you initially thought, they are going to bump into each other a lot sooner. The same principle applies on a galactic scale. New models, accounting for our true size, suggest the initial interaction could begin in under 4 billion years, maybe even 3.5. The exact timeline is still being refined, but the trend is terrifyingly clear. Bigger galaxies mean earlier contact. Here is what that collision will look like. First, the outer halos will merge, a silent, invisible interpenetration of dark matter. But the gravitational effects will be immense. Stars in both galaxies will begin to feel the pull of two galactic centers. Orbits will destabilize. Some stars will be flung out into the lonely void of intergalactic space, while others will be pulled inward toward the chaotic cores. Then, the visible disks will collide. This isn't a crash in the way we think of one. It's more like two vast clouds of smoke passing through each other. Stars are so incredibly far apart that direct impacts will be almost non-existent. But the gravitational chaos will reshape everything. Gas clouds will slam into each other and compress, triggering a spectacular burst of star formation. The Milky Way and Andromeda will light up as millions of new stars are born. For the next billion years after that first contact, the two galaxies will dance. They will spiral around each other, their elegant arms shredded by tidal forces, their stars scattered in every direction. The beautiful structures we know today will be warped and distorted beyond all recognition. Eventually, they will merge completely, settling into a single colossal elliptical galaxy, a chaotic blob of nearly 4 trillion stars. Astronomers have already given it a name, Milky Way. But will our world survive to see it? The good news is, the sun will likely be fine. It sits far enough out that it will probably avoid the worst of the chaos. The bad news? Our star will be in its death, throes by then anyway. A bigger Milky Way has moved the timeline up. The show starts sooner. And here's the thought no one talks about. We assume Andromeda's measurements are correct. What if they're wrong too? What if both galaxies are even bigger than our latest estimates? Their halos might already be touching. The collision may have already, silently, begun. In the cosmos, mass is everything. Mass is gravity. Mass is power. Mass dictates how stars are born, how galaxies form, and how the universe itself evolves. And the Milky Way just gained a terrifying amount of weight. For years, we thought our galaxy contained about 1.5 trillion times the mass of our sun. A staggering number, to be sure, with most of that being dark matter. But the new measurements, the ones that account for the galaxy's true size, have nearly tripled that figure. Our home galaxy weighs in at a colossal 4 trillion solar masses, and possibly even more. We have been living in a heavyweight champion and thought it was a middleweight. Let's try to understand what a solar mass even is. Our sun weighs about 2 nonillion kilograms. That's a 2 with 30 zeros after it. It's a number so abstract it's useless. For comparison, the Earth weighs 333,000 times less. Jupiter, the king of our solar system, weighs over 1,000 times less. In fact, every planet, moon, asteroid, and comet in our entire solar system combined barely adds up to a fraction of a percent of a single solar mass. Now, take the mass of our sun and multiply it by 4 trillion. That is the Milky Way. A gravitational titan of almost unimaginable power. So where did all this extra mass come from? Did our galaxy suddenly hit a cosmic growth spurt? Of course not. The mass was always there. We were just blind to it. The vast majority of this newly accounted for mass is dark matter, lurking in the enormous invisible halo that our old measurements completely missed. We were trying to weigh an elephant by only putting its foot on the scale. New techniques, tracking the frantic orbits of distant satellite galaxies and tracing the ghostly paths of stellar streams, finally allowed us to weigh the whole beast, and the result changes our place in the universe. More mass means stronger gravity. It means we can hold more satellite galaxies captive in their orbits. It means we can more easily rip stars from passing galaxies. It means we are the undisputed gravitational bully of our cosmic neighborhood. For years, Andromeda was considered our bigger, more massive sibling, the true alpha galaxy of the local group. But these new measurements suggest we may be its equal, or perhaps even larger. We are not the junior partner in this cosmic dance. We are two galactic superpowers, each weighing around 4 trillion solar masses, locked on a collision course. This new weight also tells us we have a much bloodier history than we knew. A 4 trillion solar mass galaxy didn't get that way by sitting quietly. It grew through conquest. It devoured hundreds, maybe thousands of smaller galaxies over billions of years. Every stellar stream in our halo is the gravestone of a galaxy that got too close and paid the ultimate price. But here is the most terrifying part. If we are 4 trillion solar masses, and 90% of that is a dark matter we can't see, then we live in a galaxy made of almost entirely invisible material. You think you know your home. You are wrong. You are swimming in an ocean of darkness, and you can't even feel the water. The galaxy does not end where the stars stop. It keeps going, far beyond the last visible outpost of light, deep into an empire of pure absolute darkness. Scientists call it the dark matter halo, a colossal spherical cloud of invisible particles that surrounds our entire visible galaxy. But this halo is not some minor feature, some cosmic afterthought. It is the dominant structure. It is the foundation. It is the gravitational cage that holds our entire galaxy together. The most conservative estimates, based on the orbits of our satellite galaxies, place the edge of this halo at around 250,000 light-years. But many models, the ones that try to account for the most distant stellar streams and the most extreme gravitational lensing effects, suggest the halo extends much, much farther. 400,000 light-years, 600,000. Some calculations, pushing the boundaries of our understanding, suggest it could reach past 1 million light-years. 1 million light-years. Let that number sink in. If that is true, it would make the Milky Way not just double its old size, but 20 times wider than the measurements that stood for nearly a century. 20 times more space under our direct gravitational control. Let's put that into perspective. Our nearest major galactic neighbor, Andromeda, sits 2.5 million light-years away. If our dark matter halo truly reaches 1 million light-years into space, and Andromeda's halo does the same, then there is only 500,000 light-years of truly empty intergalactic space separating our two empires. Our invisible borders may already be touching, two vast clouds of dark matter already beginning to intermingle, setting the stage for the final collision. We cannot see this halo directly, of course. Dark matter does not emit light. It does not absorb light. It does not interact with any form of electromagnetic radiation. It is a ghost. It interacts only through gravity. But that gravity is real, it is measurable, and it is powerful. You are inside it right now. Trillions of dark matter particles are passing through you, through the Earth, through the Sun, as we fly through this invisible sea. This new picture forces us to fundamentally change how we view the cosmos. Galaxies are not pristine islands of stars floating in an empty void. That picture is dead. Galaxies are enormous halos of dark matter, and the stars are just a sprinkle of glitter concentrated in their centers. The visible part is the decoration. The invisible part is the substance. And here is the final universe-altering implication. If our halo is this large, then every other galaxies must be too. The universe is not mostly empty space dotted with galaxies. The universe is mostly made of overlapping dark matter halos, with tiny concentrations of light we call galaxies embedded within them like seeds in a fruit. Everything we can see, every star, every nebula, every ounce of visible beauty in the cosmos is just a tiny fraction of what is actually out there. The visible universe is nothing more than an afterthought, painted onto an invisible scaffold of unimaginable scale. A million light years of darkness. That is the Milky Way. That is our home. The galaxy is spinning too fast. It should be tearing itself apart. The stars at its outer edge are moving at speeds that make no sense, speeds that should have flung them into the blackness of intergalactic space eons ago. They are breaking the law, not a law made by man, but a fundamental law of motion first uncovered by Isaac Newton 300 years ago. And nobody is entirely sure why. Here is the problem. In our solar system, everything works exactly as you'd expect. The planets closest to the sun, like Mercury, race around in a frenzy. The planets farther out, like Neptune, drift along at a stately, leisurely pace. The farther you get from the central mass of the sun, the weaker its gravitational pull becomes, and the slower you must orbit to remain stable. This is basic high school physics. It's elegant, it's predictable. And galaxies should work the same way. Most of the visible mass, the stars, the gas, the supermassive black hole, is concentrated near the galactic center. Therefore, stars in the outer regions should feel a much weaker gravitational pull and should be moving much, much more slowly. When you measure their speeds, you should get a nice, predictable curve that drops off with distance. Except that is not what happens. The rotation curve of our galaxy, and almost every other spiral galaxy, stays stubbornly, impossibly flat. Stars at the very edge of the visible disk orbit at nearly the same blistering speed as stars much closer to the core. This observation is the single greatest piece of evidence for dark matter. The invisible halo, we believe, provides the extra gravitational glue needed to hold on to these speeding stars. It's the smoking gun. Case closed, right? But here is where it gets truly strange. Even when we account for all that dark matter, the speeds are still higher than our models predict. We've found stars in the outer halo moving at 130 miles per second. Others are hitting 150. These velocities are terrifyingly close to the galaxy's escape velocity. These stars are barely hanging on, skating right on the razor's edge of freedom. Why? Why are so many stars orbiting in this precarious high-energy state? One possibility is that we are still underestimating the galaxy's mass. Maybe there is even more dark matter than our current models suggest. Another idea is that these are the survivors of ancient collisions. When the Milky Way devoured a smaller galaxy, the merger could have violently injected stars into these fast, unstable orbits, and they simply haven't had time to settle down. But what haunts astronomers is that it's not just the fast stars that are a problem. We've also found stars that are moving too slowly, stars that drift as if trapped in molasses. The larger galactic size only makes this problem worse. It means there is more volume, more stars, and therefore more of these inexplicable anomalies to account for. Physics works perfectly in solar systems, in distant galaxies, in every other corner of the universe we have tested. But here, in our own cosmic backyard, in the spinning of our own home, something is still not adding up. How many spiral arms does the Milky Way have? It sounds like a simple question, a basic piece of cosmic trivia. The answer should be a single, solid number. But the truth is, we don't know. For decades, the textbook answer was 4 major arms, elegant rivers of stars, gas, and dust spiraling out from the galactic core. But the real answer is maybe 4, or 5, or 6, or maybe the question itself is wrong. Astronomers are still in a heated debate, and every new telescope we build seems to make the picture muddier, not clearer. The classic diagram shows the Scutum Centaurus, Norma, Perseus, and Sagittarius arms. These were the bright, obvious structures, the superhighways of star formation. But then we built better eyes, infrared instruments that could peer through the thick dust that veils the galaxy's far side. radio telescopes that could map the vast, invisible clouds of hydrogen gas, and hidden structures began to emerge from the darkness. An entirely new arm, the far 3 kiloparsec arm, was found hiding behind the galactic core. It had been there all along, thousands of light-years long, completely invisible to our old optical telescopes. But the real mind-bending mystery isn't how many arms there are, but why they exist at all. Here's the problem. The galaxy doesn't spin like a solid disk. Stars closer to the center orbit much faster than stars farther out. If the spiral arms were just static clumps of stars, this differential rotation would have wound them up impossibly tight billions of years ago. Like stirring cream into a cup of coffee, the elegant spiral pattern should have been smeared out into a featureless blur within just a few rotations. The fact that they persist is a paradox. The leading theory is that the arms are not physical structures at all. They are illusions. They are density waves, regions of space where gravity temporarily squeezes matter together, triggering a burst of new star formation. Think of it like a traffic jam on a highway. The jam itself stays in one place, but the individual cars are constantly moving through it. The spiral arms are a cosmic traffic jam. Stars, gas, and dust flow into the wave, get compressed, ignite into brilliant new stars, and then flow out the other side. The wave itself persists, but the material within it is always changing. It's a beautiful, elegant theory, but observations keep finding nagging exceptions. Some arms have far too many young stars. Others seem too massive to be just a temporary wave. And the larger size of the Milky Way only deepens the mystery. There is simply more space for more structures, more arms, and more chaos. Recent maps from the Gaia spacecraft, which has tracked over 1 billion stars, reveal a pattern that is not clean or elegant at all. It's messy, chaotic, and branched, like a tree growing in a hurricane. Some astronomers now argue that the Milky Way isn't a perfect grand design spiral. It might be a patchy, chaotic galaxy with poorly defined transient arms. This would explain why different surveys find different numbers. They are all just seeing different pieces of a messy, ever-changing puzzle. If we have missed entire spiral arms hiding in our own galaxy, what other colossal structures are lurking in the darkness, waiting for the right pair of eyes to find them? Go ahead, try it. Draw a line in your mind marking the definitive edge of the Milky Way. It sounds simple enough, but it is a fundamentally impossible task. Our galaxy does not have a border. There is no cosmic wall, no signpost that says, "You are now leaving the Milky Way." The stars just thin out. They fade, gradually and gracefully, until there are only a few scattered stragglers left, and then nothing, or at least what looks like nothing. So where, in that slow, gentle fade to black, does our galaxy actually end? This is not just a philosophical question. It's one of the most frustrating practical problems in astronomy. We need a definition, a standard measurement to compare our galaxy to others. But the universe does not cooperate. It does not care about our human need for clean lines and neat categories. For years, we used the simplest definition, the optical radius. This marks the point where the brilliant visible stars of the galactic disk become too faint and sparse to see. This is where we got the old 100,000 light-year number, but this method is like trying to measure the size of a city by only counting its brightly lit skyscrapers and completely ignoring the sprawling, dimmer suburbs, let alone the countryside beyond. A more scientific and useful definition is the virial radius. This marks the true gravitational boundary of our galaxy, the point beyond which objects are no longer bound to us by gravity. Inside this radius, stars orbit our core. Outside, they drift freely in intergalactic space. For the Milky Way, this gives us our new, updated size of roughly 250,000 light-years. Much better. But even this has problems. gravity's reach is infinite. Objects well outside the virial radius still feel our galaxy's faint pull. Are they a part of it or not? Then there is the colossal dark matter halo. If it truly extends out for 500,000 or even 1,000,000 light years, is that the real edge? Most astronomers would say no. The halo fades so gradually that choosing any specific point as the boundary is completely arbitrary. It's like trying to pinpoint the exact altitude where Earth's atmosphere ends and space begins. There is no line. The air just gets thinner and thinner forever. To make things even messier, our galaxy is constantly breathing. Supernova explosions and stellar winds create massive outflows of hot gas that travel hundreds of thousands of light years out into the void. Is that material still part of the Milky Way? It came from here. Most of it will eventually fall back. But for now, it exists in a state of cosmic limbo. The truth is, the Milky Way is not an object. It is a region, a zone of influence, a gravitational neighborhood. The number 200,000 light years is our current best answer, a practical line drawn in the sand. But the deeper reality is that our galaxy has no true edge. It simply blends into the cosmos, a seamless transition from something into nothing. The Milky Way is a cannibal. Our beautiful, serene-looking galaxy grew to its current colossal size by systematically hunting, killing, and eating its own kind. For billions of years, hundreds of smaller galaxies have fallen into our gravitational well, only to be shredded, torn apart, and consumed. Their stars, their gas, their dark matter, all of it becomes part of us. This is the brutal, violent truth of how galaxies grow. It is not a story of gentle accumulation. It is a story of conquest. The gravitationally massive survive and grow, while the weak become their meals. And the evidence of our galaxy's bloody past is all around us, written in the sky for anyone willing to look. Every stellar stream that wraps around our halo is the ghost of a dead galaxy. Each one is a cosmic corpse, the stretched-out remains of a world that wandered too close. We can see this process happening right now, in real time. The Sagittarius dwarf galaxy, a respectable system with about 400 million stars, is currently being torn to pieces by our tidal forces. It is a meal in progress, an act of active consumption. Over the next billion years, its stars will be scattered and absorbed into the Milky Way until no trace of it remains, except for a few faint, ghostly ripples in the data. But Sagittarius is just the latest victim. Around 10 billion years ago, the Milky Way consumed a truly massive galaxy known as Gaia Enceladus. This was no dwarf. It was a substantial galaxy, perhaps a quarter of the Milky Way's mass at the time. The collision was cataclysmic and fundamentally reshaped our home. We know this happened because the Gaia spacecraft has found its remains. Billions of stars in our halo are moving on strange retrograde orbits, traveling backward against the normal flow of galactic traffic. They are foreigners. Chemical analysis confirms their alien origin. They have different elemental compositions than native Milky Way stars. They are the undigested bones of a conquered rival. And there were others. The Kraken merger, an even bigger collision 11 billion years ago. The Sequoia dwarf, the Helmy streams. Our home is not a single cohesive entity. It is a graveyard empire, built from the corpses and stolen stars of dozens, perhaps hundreds of other galaxies. This cosmic cannibalism creates a runaway effect. The rich get richer. Once a galaxy becomes massive enough, its gravitational reach extends farther, allowing it to capture even more victims. As it eats, it grows larger still, which in turn increases its gravitational power. It is a cycle of violence and growth that continues to this day. And here is the most profound part. You are a part of this story. The heavy elements in your body, the carbon, the oxygen, the iron, were forged in the hearts of ancient stars. Some of those stars likely belong to these conquered galaxies. Material from those devoured worlds was recycled through supernova explosions and eventually formed our sun. Our Earth, and you are, in a very real sense, an immigrant. You are made of the stardust of alien galaxies that were eaten by our own. Scientists hate being wrong, not because of ego, but because being wrong means that the entire foundation of their understanding is flawed. It means textbooks must be rewritten, calculations must be redone, and years of work must be reevaluated. The James Webb Space Telescope, launched in December of 2021, is a $6 billion machine designed to force exactly that kind of uncomfortable revolutionary moment. It was built to see the earliest galaxies at the dawn of time. Nobody expected it to completely upend our understanding of our own home, but it did. Webb's superpower is its vision in the infrared spectrum. This allows it to do something Hubble never could: see through the colossal, impenetrable clouds of dust and gas that choke our view of the galaxy. For the first time, we could peer into the hidden heart of the Milky Way, map the far side of the disk, and explore the outer regions with breathtaking clarity. And what Webb found there shattered the old picture. It found stars, billions of them, lurking in the faint outer halo where we thought there was only empty space. It resolved individual stars in the most distant satellite galaxies, allowing for hyper-accurate measurements of their orbits, each one screaming that the Milky Way was more massive than we knew. It traced the ghostly stellar streams to even more extreme distances, proving our gravitational empire extended far into the supposed void. But the knockout blow, the single piece of evidence that ended the debate, came from gravitational lensing. Using its unparalleled precision, Webb measured how the light from ancient distant galaxies was being bent by the Milky Way's gravity on its journey to us. By calculating the exact degree of that bend, Webb could weigh our galaxy directly. The number it came back with was undeniable, confirmed by multiple independent lines of evidence: 4 trillion solar masses. The old models were dead. At first, the scientific community erupted in debate. Papers were published defending the old measurements. Conferences were filled with heated arguments. But data is data. You can argue with a theory, but you cannot argue with the direct measured warping of space-time. Slowly, grudgingly, the consensus shifted. The James Webb Space Telescope had delivered an inconvenient but essential truth. The textbooks were wrong. Science, in the face of overwhelming evidence, was forced to correct itself. And Webb's revolution didn't stop with us. It turned its golden eye to Andromeda, to Triangulum, to other spirals across the cosmos, and it began to see the same shocking pattern everywhere. Our mistake wasn't a local error, it was a universal one. The Milky Way is not special. This is one of the most fundamental and humbling principles in modern cosmology. And if our galaxy is not special, then the colossal error we made in measuring it is probably not unique either. This is the terrifying implication that rippled through the astronomical community in the wake of Webb's discoveries. The chilling realization that if we could be so wrong about our own cosmic backyard, we were probably just as wrong about every other spiral galaxy in the entire universe. The cosmic census, the grand catalog of worlds we have been compiling for a century, needed to be rewritten from scratch. So researchers put the hypothesis to the test. They selected a sample of our nearest spiral neighbors, Andromeda, Triangulum, and others close enough for detailed observation, and they applied the same new revolutionary techniques. They tracked the delicate orbits of their satellite galaxies. They mapped the ghostly stellar streams left behind by ancient mergers. They calculated the true mass locked away in their vast, invisible dark matter halos. And the results were a stunning, terrifying confirmation. Every single galaxy came back significantly larger. Andromeda, long thought to be about 220,000 light-years across, swelled to over 300,000. Triangulum, the third largest member of our local group, jumped from 60,000 light-years to nearly 100,000. The pattern was universal and undeniable. We had been systematically underestimating the size of spiral galaxies across the board. The mistake was always the same. Our old methods were biased toward visible light. We drew the line where the bright, obvious stars ended, blind to the faint, scattered populations in the outer halos, and completely ignorant of the true scale of the dark matter that dominates them all. The error was built into our very way of seeing the universe. This discovery has staggering, cascading implications that touch every corner of astrophysics. If galaxies are universally larger and more massive, then our understanding of how they interact, merge, and evolve over cosmic time must be fundamentally revised. The entire cosmic web, the grand structure of galaxies strung across the universe, is denser and more crowded than we ever realized. Our most fundamental cosmological models, the ones that describe the origin and fate of the universe itself, rely on an accurate accounting of all the matter and gravity within it. If every galaxy contains double or triple the mass we thought, the entire energy budget of the cosmos shifts. We are right now recounting the universe, every galaxy, every cluster, every filament of the cosmic web. And the universe that is beginning to emerge from the data is bigger, heavier, and far more complex than we ever imagined. The Milky Way was just the first domino. Now, the rest are beginning to fall. Our cosmic neighborhood, the local group of galaxies, just shrank. Not because anything moved closer, but because its residents got so much bigger. The local group is our home, a gravitationally bound cluster of about 80 galaxies within a 10 million light-year radius. For decades, we pictured it as a vast, mostly empty space dominated by three giants, the Milky Way, Andromeda, and the smaller Triangulum galaxy, with dozens of tiny dwarfs scattered between them. That picture is now obsolete. The boundaries must be redrawn because the galaxies themselves have claimed far more territory than we ever gave them credit for. When a galaxy's size doubles, its sphere of gravitational influence expands dramatically. The neutral, no-man's land of intergalactic space that we thought separated these giants has all but vanished. Consider our relationship with Andromeda. The distance between our galactic cores is a staggering 2.5 million light-years, but that number is deeply misleading. Our new measurements show that the Milky Way's dark matter halo extends at least 250,000 light-years in its direction, and Andromeda's halo does the same, reaching back towards us. Suddenly, the 2,500,000 light-years of empty space has shrunk to just 2 million, or even less. Our invisible empires are already on the verge of contact, if they haven't started merging already. This new crowded reality has dire consequences for the smaller members of our group. The Magellanic Clouds, which we once thought might just be passing through, are now confirmed to be permanent captives, trapped in an inescapable gravitational grip. In a few billion years, we will devour them. Triangulum, once considered the third major independent player, now looks more like a satellite of the much larger Andromeda. Sitting only 750,000 light-years away from it, their halos are almost certainly overlapping. It is no longer a question of if Andromeda will consume it, but when. And the dozens of tiny dwarf galaxies adrift in the space between us and Andromeda, they are caught in a gravitational crossfire, their fates sealed. They will be torn apart as the two giants begin their final cataclysmic dance. The local group is not a collection of serene, isolated islands of stars. It is a set of vast, overlapping spheres of influence, a contested territory where gravitational borders are constantly being fought over. The very concept of a separate galaxy is a human construct, an illusion of tidiness imposed on a messy, chaotic reality. The truth is far more fluid. Our neighborhood is not a collection of distinct objects. It is one enormous, interconnected gravitational basin, and we are just now beginning to understand the true complexity of the place we call home. The star count just doubled. The old familiar estimate of 200 billion stars in the Milky Way is now officially retired. Our home galaxy contains approximately 400 billion stars, and perhaps even more. This is not a number the human mind is equipped to handle. If you were to count every single one of those stars, one per second, without ever stopping to eat or sleep, it would take you 12,700 years. Your task would have begun before the invention of agriculture, and you would still be counting today. To put it another way, there are 50 times more stars in our galaxy than there are human beings on planet Earth. You would need 50 planets, each with a population of 8 billion people, just to have one person for every star. Why the dramatic increase? It's a simple, brutal matter of geometry. Doubling the galaxy's radius doesn't just double its area, it increases its total volume by a factor of 8. 8 times more space. While the outer regions of the galactic halo are far more sparsely populated than the dense inner disk, the sheer immensity of that extra volume adds hundreds of billions of stars to the census. Most of these newly accounted for stars are dim red dwarfs, the galaxy's quiet majority. They are small, faint, and incredibly long-lived, and they hide in the darkness, easily missed by all but the most sensitive surveys. On top of that, we must now add all the stars we have stolen. Every time the Milky Way devoured a smaller galaxy, it absorbed that galaxy's entire stellar population. The Sagittarius dwarf alone contributed tens of millions of stars that now officially count as ours. 400 billion stars means, at a minimum, hundreds of billions of planets. Current estimates from missions like the Kepler Space Telescope suggest that most stars, perhaps 60% or more, have at least one planet. That gives us a conservative starting number of 240 billion planets in the Milky Way. And the number of potentially habitable worlds, planets orbiting in that Goldilocks zone where liquid water can exist, is now estimated in the tens of billions. Think about what that means. The number of potential homes for life didn't just increase. It exploded. Every variable in the famous Drake equation, which seeks to estimate the number of intelligent civilizations, just got a massive boost. This makes the search for extraterrestrial intelligence both more hopeful and infinitely more frustrating. The chances that we are not alone have statistically just doubled, but it also deepens the profound, haunting mystery of the Fermi Paradox. The galaxy just got twice as crowded. The number of potential neighbors just skyrocketed, and yet all we hear is silence. With 400 billion stars and billions upon billions of habitable worlds, where is everybody? Double the stars, double the planets, double the chances for life, and double the silence. This is the new, intensified horror of the Fermi Paradox. If our galaxy is teeming with 400 billion stars and potentially tens of billions of habitable worlds, then the silence we hear from the cosmos is no longer just a curiosity. It is a deafening, terrifying roar. It suggests that something is deeply, fundamentally wrong with our assumptions. With so many potential homes for life, so many rolls of the cosmic dice over 13 billion years, where is everybody? This is the question that haunts the men and women of SETI, the search for extraterrestrial intelligence. And the answers they consider are both profound and chilling. One possibility is the Great Filter. The idea is that there is some barrier, some incredibly difficult or dangerous step in the evolution of life that is almost impossible to overcome. The question is that filter in our past or in our future? If the filter is behind us, then we are one of the rarest things in the universe. Perhaps the leap from non-living chemistry to the first living cell is the barrier. Or maybe the jump from a single cell to complex multicellular life is the near impossible step. If this is true, then we are among the first, and the galaxy is a vast empty frontier waiting for us. But the other possibility is far more ominous. What if the Great Filter is ahead of us? What if intelligent life is common, but it inevitably destroys itself before it can become a star-faring civilization. Nuclear war, catastrophic climate change, a rogue artificial intelligence, a genetically engineered plague, the list of potential self-inflicted apocalypses is long. In this scenario, the silence is a graveyard. The galaxy is full of the ruins of civilizations that reached our level of technological prowess and then failed their final test. Of course, there are other stranger possibilities. Maybe they are out there, but they are deliberately hiding. The dark forest theory suggests that the universe is a dangerous place, and the first rule of survival is to never, ever reveal your location. To broadcast a signal into space is to scream, "Here I am, come and get me," to older, more advanced, and potentially hostile civilizations. In this terrifying vision, the silence is not one of emptiness, but of fear. Or perhaps we are simply too primitive to recognize their signals. We scan the skies for radio waves, while they might be communicating with neutrinos or gravitational waves or some form of physics we haven't even discovered yet. It would be like trying to join a global fiber optic conversation using a pair of smoke signals. The new larger Milky Way doesn't give us the answer. It only makes the question more urgent. The James Webb Space Telescope is now hunting for biosignatures in the atmospheres of distant exoplanets, the chemical fingerprints of life. The search continues, but the silence remains. Are we truly alone in this vast, crowded cosmos? Or are we just one lonely voice in a cosmic conversation that we haven't yet learned how to hear? So, let's step back. We started this journey with a simple, comfortable map of our home. That map is now in ruins. Let's try, with everything we have learned, to sketch the new one. What is the Milky Way, really? It is a barred spiral galaxy, yes, but that is like describing a human being as a collection of cells. The truth is far grander and stranger. Our home is, first and foremost, a colossal halo of invisible dark matter, a gravitational titan weighing at least 4 trillion times more than our sun. This halo is the true galaxy. It is a sprawling, spherical empire of darkness that stretches at least 200,000 light-years from edge to edge, and perhaps much, much farther. Embedded deep within this invisible superstructure is the part we call home, a swirling disk of some 400 billion stars, organized into a messy, chaotic pattern of unstable spiral arms. This structure was not born, it was built. It was assembled over 13 billion years through a relentless campaign of galactic cannibalism. Our home is a graveyard, populated by the stolen stars of hundreds of smaller galaxies that were hunted down, ripped apart, and absorbed. We see the ghosts of its victims in the great stellar streams that wrap around us, and we are made from their recycled stardust. We live in a kingdom built on conquest. Within this violent, sprawling empire, there are potentially billions of worlds that could harbor life. It is a galaxy crowded with possibility, yet wrapped in a profound and unnerving silence. And we are adrift inside of it, on one tiny planet, in one unremarkable solar system, trying to map the whole thing from a single, obscured vantage point. This new portrait of our home is humbling. It is terrifying, but it is also a profound triumph. Science is not a collection of unchanging facts. It is a process of getting progressively less wrong. We had a model, new evidence from incredible instruments like the James Webb Space Telescope shattered that model, and now we have a new one that fits the evidence better. It is a testament to our relentless, insatiable curiosity, to our courage to admit when we are wrong, and our determination to keep looking, to keep measuring, to keep drawing the map, even when the territory seems impossibly vast. This new portrait is not the final one. It is merely the latest draft, the best understanding we have today. In 10 years, in 50, it will change again. The measurements will be refined. New discoveries will add new layers of complexity. The one thing we can be certain of is that our galaxy is, and always will be, more magnificent and more mysterious than we can possibly imagine. So why does any of this matter? Why do we, a fragile species on a speck of dust, spend our lives and our fortunes building colossal machines to gaze into the darkness? Why does it matter if our galaxy is 100,000 light-years wide or 200,000? The number itself is meaningless. It's an abstraction our minds can't truly hold. It matters because the act of measuring the universe is the act of measuring ourselves. We are, as far as we know, the only part of the cosmos that has woken up and is trying to understand the rest. Every time we point a telescope at the sky, we are shouting a question into the great silent void. And the answers that echo back tell us not only about the stars, but about the nature of the minds that are asking. For 70 years, the echo that came back told us we lived in a modest, well-lit home, a manageable, comprehensible place. The new echo tells a different story. It tells us we live in a sprawling, invisible empire of darkness, a kingdom built on violence, a structure so vast and ancient that our existence within it is a fleeting, infinitesimal flicker. It tells us that our cosmic loneliness is either far more profound, or our potential family of neighbors is far larger than we ever believed. It redefines our context. To be human is to stand on a shore and stare at a boundless ocean, and this discovery has just revealed that the ocean is twice as large as we had mapped. This knowledge doesn't make us smaller, it makes us grander, because it is our curiosity, our relentless refusal to accept the simple answer, that revealed this truth. We are the universe's way of knowing itself, and this single staggering correction to our cosmic address is one of the most profound acts of self-awareness the universe has ever achieved. The map will never be finished, the final number will never be written, but the glorious, endless human act of trying to draw it, of trying to measure the echo, is what gives our brief moment in the light its meaning.